Well, now we start a new topic. We know the difference between particles and waves. Waves interfere. Waves produce interference pattern. Particles don't. Or we thought so. Turns out, particles make interference pattern as well. Well, this is a very now standard experiment, and some classes actually have a lab like that. They actually measure the wavelength of particles in this tube. What kind of particles? It's an electron gun. It's like very old TV. So electrons traveling inside this tube. Well, of course, to make electrons traveling, first I need to plug it in, turn it on. This camera is really, really bad. Let's see if we can see anything. So what we see now is a bright spot right in the middle. Well, this we can explain easily. Electrons traveling straight ahead, just hit the screen, and we can see where it's happening. If you look closely, or if you sit closely, you can actually see now some rings around. This is practically the same interference pattern we would have for light traveling through a hole. Same rings. So this is a diffraction pattern. What can we measure from the diffraction pattern? We can measure the wavelength of this wave. We just need to know the distance between the screen and the slit, and we need to know, well, the distance from the central maximum to the first maximum or to the first minimum, and that's it. And use our equations, and that's what people do in the lab. Turns out that they can actually calculate the wavelength. And that's supposed to be the wavelength related to the electrons traveling in this tube. Well, on the other hand, to accelerate electrons, we apply an electric field. We just use a power supply. So we can calculate the energy, kinetic energy, momentum, speed of those electrons. And for those experiments give us a very, very interesting result. Turns out that the wavelength of those particles, electrons or all other ones, is just inversely proportional to the momentum. The coefficient, this constant, is very, very small in its value. It's 10 to the negative 34 if we use International System of Units, joule per second. So that's why this phenomenon works only for really, really small particles. If you were calculating the wavelength of a baseball or a ping pong ball, you would get so tiny number that we just couldn't measure that, never. However, for a really, really small particles, when the mass is really small, and if we make them move relatively fast, we can actually reach the wavelength, which is measurable, like we just did. And that's true not just for electrons, that works for all particles. Okay. No, yes. So one single electron is a particle. When it hits a screen, it makes a small explosion. If we had a photofilm, that's what we see, after 100 electrons hit that screen. But if we have more and more electrons, we can see clearer and clearer interference fringes. So electrons, on one way, are particles, but on the other hand, waves. How can we merge these two notions? Well, the idea is simple. They are both. So basically an electron or a proton or a photon or any other particle is just a new physical object. We call it a microscopical object which has both properties. Properties of waves and properties of particles. So as a particle, it has mass, energy, it could be located somewhere, sometimes. As a wave, it also has the wavelength, frequency, etc., etc. So on the micro level, all those objects have everything. And of course, we have to know how to relate. Well, this is basically an expression which relates to different worlds, a particle world and a wave world. And now we can use all equations from both worlds together. Well, this is one of the examples of a calculation of a wavelength for any particle. Yeah, there's no number given for anything here. So that's kinetic energy. This is how we should calculate momentum. If we know the momentum, well, this combination is used just for convenience because this product is some fixed number. And here on the bottom, this product equals to, well, again, very simple combination. And if you look at this, you can see the faster the particle is moving, the larger its kinetic energy, the smaller its wavelength. This is a numerical example of a calculation. Here we actually using International System of Units, and that's the baseball. So in this particular problem, the wavelength of the baseball is 10 to the negative 12 of a meter. We cannot practically measure this. Well, and this is a de Broglie equation of some particle with a given momentum, 1 kilo electron volt. Well, this calculation tells us a value of a specific constant. So here, 1 kilo electron volt over c, speed of light. So if you want to calculate the wavelength for this particular particle, you have to use this equation. That's what we call de Broglie equation. But to simplify our calculations, we multiply numerator and denominator by c. What does it give us? Here on the bottom, P times C equals 1 kilo electron volt divided by C times C, and C cancels, so 1000. And here on the top, we have this product, Hc. H is a Planck's constant, it's a constant. C is a constant. So if you multiply two constants, we will always have just a new constant. And the value of this constant is, again, a very convenient number, 1240. 1240 what? Nanometers. So if you're using this constant, that gives you very quickly the result for the wavelength in nanometers. That's it. It's just two shortened calculations, 10 to the negative 9 of a meter. Well, how big do you think is atom? Well, of course, different atoms have different sizes, but it's it's kind of close to that. 0.3, 0.5. So this wavelength is actually pretty big. If this wavelength is of the size of the atom, so a particle with this wavelength would be diffracted by atoms, and that's what we saw in this experiment. If we had a baseball, that wouldn't work for the baseball anymore. All right. Well, this is an example of a problem related to this particular experiment. How would we do this problem? Well, first of all, electrons getting accelerated. Well, for this particular problem, we assume that the speeds actually much smaller than speed of light. So for kinetic energy, we still could use mv squared over 2. So to calculate the kinetic energy here, we would have to set it equal to work done by electric field. And that would give us the speed of, well, if it's mv squared over 2, we could calculate the speed of these electrons traveling through the target. Diffraction is happening here. And if we know the speed, we could also use this expression to calculate the wavelength. Sometimes, actually, it's much easier to rewrite this expression in terms of kinetic energy. Again, for relatively slow electrons, we could rewrite m squared v squared 2m p squared over 2m. We could rewrite kinetic energy in terms of momentum. So in that situation, we could rewrite the de Broglie wavelength in terms of kinetic energy. That's going to be constant over. To calculate the momentum, we would have to calculate square root of 2mk. And we actually can plug in this expression if we need, which is actually equal to this expression. So for the wavelength, a shortest way to get it is 2meV. Planck's constant, 2 times mass times kinetic energy, which is supposed to be equal to work done by electric field. And if you use these numbers, you actually can get calculatable results. We don't need a calculator to finish this calculation. Well, if all particles have properties, wave-like properties, it's kind of natural to assume, at least now, that photons might have particle-like properties. Well, for photons, it's kind of been back and forth. Newton and all Newtonians used to think light is made of particles. Then Huygens came, Thomson, Arago, Fresnel, and everybody had been convinced light is not made of particles, it's a wave. Then 19th century came, experiments on photoelectric effect, Max Planck, Hertz, Einstein, and turns out light is made of particles. So what is it? Well, now we know. It's both, basically. In one kind of experiments, light shows its wave properties. In other experiments, Light shows its particle properties. That's it. So basically there is no difference between light, protons, electrons, although one exception, light doesn't have rest mass, it travels at speed of light. That's why it's light. And here, if we combine all possible expressions together, we can write so many different equations we could use for light. Well, we could think of this as a particle, we call it a photon, like this, or we could think of this as a wave. So we can assign all those variables we can. You assign to particles and to waves. Wavelength, kind of mass, but not a rest mass. Frequency. Well, speed, momentum. For light, equation is actually simpler. And for light, again, the higher the frequency is, which means the shorter the wavelength is, which means that the shorter the photon is, the more energetic that light is. Energy is proportional to the frequency, inversely proportional to the wavelength. And now we can use this fact to, well, this is just an example of a calculation. This is another example of a calculation which involves another convenient unit for Planck's constant. For the Planck's constant, sometimes instead of using joules, again we use electron volts. In that case, in electron volts times a second, the value of the Planck's constant close to 4 times 10 to the negative 15. So we can use this number to calculate the energy of photons in electron volts. It's much easier than in joules. You just take this number, the frequency, and you multiply it by 4 times 10 to the negative 15. Negative 15 and 14, that gives you just 10. So this calculation would give you that, well, at two ends of the spectrum, the energy of visible light is somewhere in between 1.8 electron volts and 3 electron volts. Red light, the visible light with the lowest frequency, has the energy close to this, and the violet close to this. So you see, the visible spectrum is also very narrow in terms of the energy as well. So we are really lucky that this very narrow feature of light actually is available to us. Well, if we have many photons, we just need to multiply the energy of a single photon by the number of photons, and that gives the intensity of light. We can explain many experiments in terms of particle-like properties of light. For example, light pressure. In terms of particles, it's really easy to understand what's happening. When light is bouncing off of a mirror, it transfers some momentum to it. Even if light getting absorbed, still it transfers some momentum to it. And that's how the pressure works. And this is my first and only question for today. Let's say you have a surface which has one side is shiny and another side is completely black. So this side reflects all the light off. This side absorbs. So in which direction the net force acting on this plate gonna point? Left, right, or there is no net force? Okay. Number 2. What's number 2? Left. Of course, because we know from mechanics when particle actually bouncing back off the surface, it transfers the momentum twice of the momentum which is transferred when the particle is absorbed. So we have a stronger force pointing to the left. Well, light is very important because of lasers, and lasers now are everywhere. We can explain two very important phenomena in terms of light, particle properties of light. First phenomenon, Compton effect. Well, basically, this is what it is. Here. When light encounters an electron, it's getting deflected. But more importantly, it changes its frequency. And classical theory could explain it correctly. But from a quantum point of view, it's a really simple phenomenon. What we really need to do is this. There's an electron. Well, let's say it's at rest. And there is a photon. In terms of the photons, it has a momentum and it has energy. So when we have two objects colliding, like two balls, we can apply two laws. The first is the law of conservation of energy, and the second one is the law of conservation of linear momentum constant. We don't have to do this math. It's actually a pretty simple math. We just need to compare what's happening before the collision and after. That's the picture for before the collision. After the collision, the photon might be scattered away, and the electron might be scattered again in other direction. However, now, well, so that's electron, energy of photon, the energy of the electron, resting energy. That's going to be the new energy of the photon. That's going to be the new energy of the electron. Energy before and after equals, that's the first law we can apply. The second law, the momentum. Again, this is the momentum of the photon before the collision. This is the momentum of the photon after the collision. And that's the momentum of the electron after the collision. And if we add them up together, after the collision, we should get the initial momentum of the system. What does it tell us? It tells us that, well, since electron starts moving and the total energy is conserved, the photon always loses some energy. So the energy of the photon after the collision is always less than the initial energy of the photon. But energy of the photon is related to the wavelength. That means scattered photon always has a different wavelength. How different? Well, the energy is inversely proportional to the wavelength. If it loses energy, that means the wavelength should go up. It should be higher. And that's what experiments show. The Compton effect looks like from a quantum mechanical point of view. A photon hits an electron. We call it a collision. So when physicists try to explain this phenomenon from a classical point of view, electromagnetic wave is traveling. It encounters an electron. Electric force starts acting on electron. Electrons start wobbling and oscillating with the same frequency. And a moving, oscillating electron generates a new electromagnetic wave. It interferes with the old one. However, every time when you carry out a calculation like that, you always get the same frequency in the result. Experiments have shown that the frequency changes. Plus, it depends on the angle. And now we know the easiest and very actually simple explanation is treat light as particles, as photons. And if you apply law of conservation of energy and law of conservation of linear momentum, you can derive this equation for the wavelength shift. And if you look at this expression, cosine is a limited function. Well, cosine itself has values between -1 and 1. That means the shift also is limited. You could apply the law of conservation of energy and plot a graph for the energy of electron depending on the energy of the photon. Here, there's an example of a calculation. Let's say you have a photon with this particular wavelength before the collision. We know after the collision, when the scattering is happening, wavelength, well, cannot decrease in its value. The change always is positive. So the new wavelength turns out to be 8.43. And if we use the law of conservation of energy, we can calculate the kinetic energy of the electron after that collision. Now, if you look at this graph, can you say, well, can the photon bounce back? Bouncing back means that it reverses its direction. Yes, it can. This corresponds to the angle of 180 degrees. So, photon has been traveling like this, and now like that. So the change in the angle is 180. That's possible. Now my question to you is, well, that's the law of conservation of energy. Would it possible that after the collision, the photon gives away its energy completely? So initial energy is getting completely transferred into kinetic energy of the electron. Is it possible or not? So can a photon disappear during the collision? If you think yes, it can disappear, it can transfer all the energy to an electron. You can press 1. If you think it's impossible, you can press 2. Just make your mind. And tell me what you think. Well, the right answer is no. But why? The law of conservation of energy seems working fine. Yeah. You can set that to 0, so why not? However, if you set the photon energy to 0, that means you have to set to 0 the frequency. If you're setting frequency to 0, the wavelength is supposed to be infinitely large, so inversely proportional to frequency. So this term is supposed to be equal to infinity, which is impossible because this function is limited. Well, the maximum value for this function is 1 minus -1, which is 2. So it's 2h over mc. That's the maximum value for this particular change in the wavelength. So it can't be larger than that. And of course, it cannot be infinitely large. So electron cannot absorb the whole energy, take away the whole energy from the photon. There is always a photon before and after the collision. Now, can this photon stop? Well, no. If you remember from Wednesday, we had an example of calculating the mass of a particle traveling at the speed of light, or the speed of a particle which doesn't have any mass. That's the photon, and the photon can't have a speed lower than the speed of light. It's a light particle, so it always is traveling at the speed of light. So it can travel 2.9 or 2.8. Of course, it can stop. Well, this is just another example. If you calculate the difference between these numbers, the change in the wavelength, that will give you this number 2.03, which is actually equal to this coefficient. So, in this example, since the change in the wavelength is equal to h over mc, that means this combination should be equal to 1. That means the cosine is supposed to be equal to 0. So in that case, that gives you the angle of 90 degrees. So when the change in the wavelength equals exactly 1 constant wavelength, in that case, the picture looks like this. After the collision, after the scattering, the photon travels at 90 degrees angle relative to its initial velocity. What is happening to electron? Well, that's a different question. So we're supposed to say that since the linear momentum is concerned, this is the momentum of the photon before the collision, which equals momentum of the whole system, because electron doesn't move yet. And that momentum is supposed to be equal to the momentum of the photon after the collision plus the momentum of the electron after the collision. So if you want to calculate the momentum of the electron after the collision, what do? We have to use vectors. It's supposed to be, actually it's supposed to be this. This minus this. We have to take this arrow and we have to subtract that arrow, which in terms of arrows equals this plus this. We just have to reverse, invert the vector. So two arrows like that give us the resultant, which means in this situation electron actually going to be, well, traveling in some direction, and this momentum is going to be having two components, the x component, the y component. The question is, what can you say about the x component of the momentum of the electron? Well, again, that's the momentum of the photon before the collision. After the collision, electron should have a momentum with two components, px, py. So, px could be greater or equal or less than the momentum of the photon before the collision. So what do you think about it? If you want to compare the momentum of the electron after the collision, and the question is about x component only, okay. Well, again, the majority gets it right. It has to be equal to. It has to be equal to the components of the photon. Again, it's just an application of the law of conservation of linear momentum. The x component of the momentum of the electron should have the same magnitude, the x component should have the same magnitude as the momentum of the photon before the collision, and the y component of the momentum of the electron should have the same magnitude as the momentum of the photon after the collision. So these two arrows, one up and down, cancel each other out, and the total momentum of the system doesn't change. And this actually situation not related to quantum mechanics, or it's not related to special relativity. No. It's just how we deal with vectors and how we apply a law of conservation of linear momentum. Now we're going to talk about the next phenomenon related to particle properties of light. Photoelectric effect. Well, when a photon encounters an electron resting in a space, there is always a collision, and the electron always travels in some direction after a collision. However, in real life, those electrons normally located inside something, like inside a metal plate. What is happening in that case? Well, we could say this is just more complicated case of Compton effect, but historically it's been described completely independently. What we can assume is that if that photon kicks it really hard, in that case, electron actually might get ejected. And we could see some electrons above the surface of this metal plate. However, if the photon is not very strong, doesn't give a strong kick, doesn't provide much kinetic energy, in that case, electron would not have much kinetic energy to leave this plate, because, well, it's a real object. It also has protons, which attracting electrons. So if we want to make electron leave this object, it has to overcome the force of attraction. So when it starts happening, we call it a photoelectric effect. For the photoelectric effect, we always can apply the same law of conservation of energy. So first we need to say that different materials have different properties, and in different materials, electrons need to spend more or less energy to actually travel to the surface. That amount of energy we call the work function. And work function depends on the properties of atoms. This applet demonstrates what is happening when we change the frequency of a light. Right now, well, I am increasing the frequency. The frequency is proportional with energy, so more frequency, more energy, and at some point, the energy of the photons become equal to the work function with the material, this red bar. What has happened after that? After that, we start observing some electrons leaving this plate. So before that happened, all electrons remain inside, but now we observe some electrons outside of this plate. And those electrons actually traveling, they have some kinetic energy. How can we calculate that kinetic energy? The law of conservation of energy says it's supposed to be equal to the difference between the energy photons supply to electrons and the amount of work electrons are supposed to do in order to leave this plate. Law of conservation of energy, that's it. Well, of course, in general, when electrons are moving away, they don't have to always travel by the shortest distance. They can keep wandering around for a while. So this is actually the maximum value of kinetic energy. Some electrons could lose more energy when traveling to the surface. So in actual experiment, we could observe electrons with different kinetic energies, but the maximum value is always provided by this law. And this is Einstein's law for the electric effect. He got a Nobel Prize for this. Because at the time it was really, really hard to accept the fact that light actually is just a particle. Well, let's take a look at an experiment. Let's see if it works today. You know what it is, electroscope, and we know how it works. All we need to do is just take two objects, rub. This is our old friend Flamingo. Worked hard for nothing. Now I want to scratch off some electrons. I know it's kind of like PVC rubbed with silk, so the flamingo is supposed to be negatively charged. The silk is supposed to be positively charged. And when I rub the flamingo against this plate, which is zinc, I'm transferring some electrons from flamingo to this zinc. And we can observe the charge. We know it's supposed to be negative. We can use a light. If I shine a light on a plate, nothing is happening. I can try something much more intense, like a laser pointer.
altogether nothing. Now I have a very special lamp, ultraviolet lamp. See, there is a kind of, not really, well, if you look here on the bottom, you can see some kind of a greenish color. That means it works. And this light does something completely different. What's happening? Well, what is happening is that visible light doesn't have much energy to actually kick out electrons. Visible light has a lower frequency, but UV light has a higher frequency, and for zinc, this frequency turns out to be high enough to eject electrons of this zinc plate. And that's what the photoelectric effect is about. Since we know what it means, and since we know the equation, now we can solve different problems, answer different questions. Well, what is happening to the work function? In this experiment, well, basically, they're different. This is the easiest kind of photoelectric experiment. In this experiment, photons disappear. So the part of the energy of the photon is transferred to an electron, and the part disappears in this work function. What's happening? Well, we know what's happening. This zinc plate becomes a little bit hotter because, well, electrons traveling around, kick around other electrons or nuclei, and some more kinetic energy getting transferred to the whole plate. More energy, E equals mc squared, is getting hotter, it's getting heavier. Eventually, we can say that in this situation, a portion of the energy is getting transferred to the mass of this plate, which is kind of a neat fact. Now, work functions, of course, have been measured for all major materials. Let's say that you using the light with photon energy 3 electron volts. What does it mean, 3 electron volts? Well, you always can multiply by 1.6 times 10 to the negative 19 and get joules. But you get really, not really convenient number, 10 to the negative something. So that's why we usually use electron volts. So if you use this light and you shine it at, let's say, lead, yeah? What's going to be happening? Are you going to be seeing electrons ejected of lead or not? The work function for this element is 4.25. The energy of a single photon in that light is 3. So, kinetic energy of the electron is supposed to be equal to 3 minus 4.25. Can kinetic energy be negative? No, never. So, that's impossible. In this situation, photoelectric effect cannot be happening. But if you use the same light and you shine it at potassium, in that case, what? Wherever, 2.75. 3 minus 2.75 greater than 0. Kinetic energy is positive. It happened. So, I don't know English name. So, this is an example of calculation from the classical point of view. You don't need to go into the details. It's not important. What's important, what's interesting is that a classical calculation would give you this number of seconds. thousands of seconds, so it's hours of time to eject electrons. In real life, it's happening instantaneously. So the classical model doesn't work. That's one of the proof of that. Well, another neat fact is that, well, basically the same mechanism explains how our vision works. Why cannot we see, for example, radio waves? A radio wave is an electromagnetic wave, so again, we can calculate the energy of each single photon. But turns out that energy of those photons is not high enough to trigger our vision. Because to trigger the vision, light is supposed to eject the electrons to start current traveling through our neural system. When it's not happening, we don't see anything. Intensity of light, of course, is related to the number of photons. Well, the intensity is energy traveling through meters squared per second. That's what we call intensity. So if we know the energy of a single photon, we just have to multiply by the number of photons traveling through a square meter each second, and that will give intensity of light. So if we want to change intensity, we have two ways to do that. Number one, we can change the frequency. Number two, we can change the number of photons. How does it affect maximum kinetic energy of electrons? Well, it depends on what we're changing. Let's say we're increasing the frequency. If we're increasing the frequency, that means we're supplying more kinetic energy to electrons. Let's say we're increasing the number of photons. In that case, the frequency doesn't change, and that doesn't affect the maximum kinetic energy of electrons. But what does it affect? Well, again, in the simplest case, one photon ejects one electron. So if we change the number of photons, we change the number of electrons ejected of the plate. That's it. But that's a straightforward question. Backwards question. If we double the intensity, what happens to kinetic energy of the electrons? Let's see what you think. I am telling you that in this experiment, I am doubling the intensity. And my question is, what is happening to kinetic energy of that ejected electron? 1. Well, let's say getting larger. 2 doesn't change. 3 getting lower. 4 not sure. Okay, well, I don't like it. Sorry. You're supposed to ask me, how did I do that? I just said, I have doubled the intensity. How? There are 2 ways to do that. I could double the frequency. So I could replace one light with another light. Or I could double the number of photons. So instead of changing the frequency, I would crank up the brightness. Or I could make a combination, changing the color and intensity, number of photons. So depending on how it exactly happened, the result is different. If I do not change the number of photons, but I am changing the frequency, again, in this case, I am changing the kinetic energy. However, if I do not change the frequency, if my change in the intensity happens because of the change in the n only, in that case, it doesn't affect the kinetic energy. So you're supposed to tell, without additional information, we don't know what is happening to kinetic energy. So the right answer is 4, not sure. See? Okay. Now, well, this is just a sample of a straightforward problem. If you know the work function, and well, first you want to calculate the cutoff frequency. Then you should figure out what's happening with electrons when the frequency was higher or lower. This is the cutoff frequency. If you're using light with the frequency lower than that, electrons stay inside. That's it. Because they don't have energy high enough to be ejected. To calculate the minimum value for the frequency, all you have to do is setting maximum kinetic energy of electrons to 0. So kind of that's a situation which divides the case with electrons staying inside and electrons moving outside. So basically we say, okay, they kind of get to the surface. They're already outside of the plate, but they lost all the energy traveling out, so there is no kinetic energy yet. If your frequency is higher than this value, in that case, kinetic energy is not 0 anymore, it's some positive value. If the frequency is lower than the minimum, or we call it cutoff frequency, lower than that, there is no photoelectric effect happening. All electrons stay inside. What about wavelength? If you know the cutoff frequency, can you calculate the cutoff wavelength? Yes, of course. The wavelength is equal to the speed of the light divided by the frequency. So, let's say you're using the light, well, this is a critical wavelength related to the critical frequency. Let's say you're using light with a wavelength larger than critical. What's going to happen? Larger frequency means larger wavelength, larger wavelength. Larger wavelength means lower frequency. For this case, the frequency is lower, the energy is not high enough, nothing is happening, that's it. Well, this is below visible spectrum, so we couldn't see it. If we used the light with a higher frequency, we could calculate how much kinetic energy electrons would have. And a very convenient way to analyze the photoelectric effect is using graphs. For this particular function, it looks like a linear function, y equals mx plus b. At the linear function, we know everything about these kind of functions. So if you use actual units, in that case, this slope of this line is supposed to be equal to the Planck's constant. And that actually gives a very straightforward method to measure Planck's constant. However, much easier using a different unit. Instead of using frequency, we could use energy of photons. So, the law would look like this. Maximum kinetic energy equals photon energy minus work function. This equation mathematically equals to this simple linear equation. That's it. The slope of this function equals to what? 1. So this angle is supposed to be 45 degrees. This distance depends on the work function. Well, below that critical energy, there are no photons. So this graph actually doesn't go down. It ends here because kinetic energy cannot be negative. However, these values, these or this, supposed to be equal to the work function. It's just a pure mathematical fact. So for example, if you look at this graph, that gives you the work function for the material number 1. This graph gives you the work function for the material number 2. But if you look at the graph and it looks like this, you know it's wrong, just plain wrong. Because if you're using energy, the angle must be 45 degrees. It cannot go like that. The angle will be must 45. All right, must be 45.
Let's start from some questions. Well, this is an example of a calculation from last week. Straightforward calculation gives the kinetic energy, maximum kinetic energy for the electrons ejected by light of some zinc plate. The question is, if we double the frequency, does it mean we also double the maximum kinetic energy of the electrons in that experiment? So, specifically saying frequency is doubled. Kinetic energy, is it doubled or no? So, if you think it is going to be doubled, your choice is 1. If you think it's not going to be doubled, your choice is 2. About 50-50. Well, this is not really related to physics. It's more related to mathematics, because when you're using an equation like that, a linear equation, well, in mathematics, we write it like this. It's not a direct proportionality between y and x. There is b. Only when b is 0, doubling x doubles y, or tripling x triples y. However, b messes it up. So because the work function is never 0, the work function is never 0. So your graph for kinetic energy as a function of frequency looks like this. So it doesn't go through 0. So what the question is about, basically this. Okay, that's your particular relationship between the maximum kinetic energy and frequency. Well, it could be also the photon energy. The only difference is
we use frequency, this slope equals the Planck's constant. When we use photon energy, this slope equals 45 degrees. That's it. So, but anyway, the original calculation relates a particular frequency or a particular energy of the photon and particular kinetic energy. Doubling frequency or doubling energy means that you're changing this twice. So this is your new value, doubled. The corresponding value for maximum kinetic energy is going to be this one, and you can look at it. And the graphic's not doubled. Well, if you would need to figure out what's actually happening, you would have to calculate. Where am I? Oh. You would actually have to calculate the new value. Well, but it wouldn't be double, it would be between double and the initial one, because you're subtracting a little bit. You're subtracting a little bit of work energy. Now here, the next question is again about graphs. Let's say this is a particular result of a particular experiment. So you run an experiment. And the question is, which of these graphs, 1, 2, 3, 4, actually, probably say, better say 2, 3, 4, 5, which of these graphs are definitely wrong, or definitely wrong? You can choose one. If you think the graph number 2 is wrong, you can press 2. If you think graph number 3 is wrong, you can press 3, etc., etc. So, which there's at least one wrong graph. Of course, you know for sure this is a correct graph. So the red line represents correct graph. Okay. 38 plus 25. More than 50%. Good. Well, first of all, you cannot press 2 or 3 when you're answering about a wrong graph. Because technically, there's nothing wrong with lines like this or like this. This question is about the slope. For all graphs, or in all experiments, this slope equals the same value. Planck's constant, if you use frequency, or, well, the slope is 1, angle 45 degrees, if you would be using the photon energy. If you're changing the material, that means you're changing the work function. And the work function might be larger or smaller, that's fine. However, the slope cannot be different. So, these are 2 wrong graphs. You could choose 4, you could choose 5. These are, well, fine graphs. Incorrect. Another question. So, we have 2 lasers. The red one, the green one. What we know is that when we use a red laser, we absorb electrons emitted. So, photoelectric effect does happen for the red laser. Now, well, that's red, electrons getting ejected, red. Question is, if instead of a red one, we're going to be using green one. observing photoelectrons in that situation. So if you think definitely yes, we can press 1. Definitely no, press 2. Well, it might depend on something else. Have I expected many people today? I should have taken my evaluation today. Well, let's see. Definitely yes is the correct answer. Definitely yes. In that situation, when we replace a green laser with a red laser with a green one, so we increasing the energy of photons. Maximum kinetic energy was equal to energy of red minus work function, and it was greater than 0. So if you're increasing this term by going from low frequency to higher frequency, you're increasing this term as well. So you're going to be observing actually more energetic electrons emitted of the plate. Now, a different question. Now what we do is this. Initially we've been using the green laser, and actually we've been observing the photoelectrons. Now we're replacing the green with red. Same answers. So far, not learning anything new, just looking at several possible questions related to Einstein's law for a photoelectric effect. Good. Now we cannot say for sure, because what we're doing now, basically on a graph, that's the maximum kinetic energy, photon energy. This is the work function. We've been somewhere here because the problem says we are observing some electrons. So kinetic energy is greater than 0. And now in this problem, we're moving in the region of lower energies. And we don't know how low do we go because we don't know the work function. If we knew it, we could say, if we knew the work function, we could say for sure what would be happening. But since we don't know, we don't know if the red laser is actually here or here in terms of the energy. So we know for sure the energy is getting lower. However, how low? We don't know. So in this situation, maybe, if the energy of red light is still greater than the work function, yes, we would observe some electrons. Less, we wouldn't. And one more. Read carefully what is happening. Again, we use the red laser first. And we, again, observe the effect. And now we want to replace the red with green. However, the intensity of the light doesn't change. So we do something else. What is happening to the number of photons? Well, each photon ejects one electron, so the number of ejected electrons is equal to the number of photons traveling per square meter every second. So, what do you think now? Okay, number 2 is most popular. So let's see. That's what the most popular answer. Well, first of all, that is wrong. It can be correct. However, this also can be correct, because from two questions before, we know when we replace a green laser with a red laser with a green one, photoelectrons getting emitted. So it's either this or this. The intensity of light is proportional to this product, frequency and the number of photons. So when you're increasing the frequency, but you keeping the intensity, that means the number of photons is supposed to get smaller than before. If number of photons getting down, that means the number of ejected electrons also should get down. Any questions? So remember, I mentioned this possible situation. When we change the frequency, we could do it differently. We could do it either by changing when we change the intensity, we could do it either by changing frequency, or we could do it by changing number of photons. So if we know what's happening to intensity, it doesn't necessarily mean we know what's happening to frequency or number of photons. If we combine two information, in this problem, the information number 1, what is happening to intensity, information number 2, what's happening to frequency, that gives the way to figure out what's happening to number of photons. All right. Now, this is one of the standard setups for this kind of experiment. We have a kind of bulb, of course, vacuum is inside, and here we have a thin layer of some material, in that case potassium, and we shine different light, and we use, for example, light filters, and now the yellow light with this wavelength is shining at this potassium plate. What is happening? Nothing. If electrons would be emitted, we would observe some current in this system. Well, this would just be kind of amplifier, and here we would actually see some measurements. Multimeter would give you a value for current in, well, milliamps. But it's not happening. What does it mean? It means the energy of these photons is below the work function of the potassium. So what could we do? We could replace a material, for example. Now we can see we observe photoelectrons. There is a current. through. What else could we do? Well, by replacing the material, we've decreased the work function. We could increase the frequency, use the light with shorter wavelength, green, and now we observe the photon effect happening. If we replace green with even more energetic light, of course, we're going to be observing the presence of the photoelectrons. But there is some difference. This battery applies a potential difference between those two electrons. So if I apply some voltage between these two electrodes, what will be happening? Well, that's an electron. And if I apply a negative potential here and a positive potential here, that electron will be traveling to the left. That will be increasing the current in the system. My connection is actually different. So an electron is emitted here. And we are applying a positive potential here and a negative potential here. This electric field tries to bring electrons back to the plate. So when I increase the potential difference, what is happening to the current? It's going down, it's getting down. Because when I make this potential difference higher and higher and higher, less and less electrons actually getting through this space, and eventually I can find the critical value for the potential when the current becomes zero. That means no electrons now actually getting through. Light makes electrons out. Electrons are emitted. However, electric field brings them back. This particular potential has a name. We call it a stopping potential. It stops electrons from reaching across this space. And of course, the stopping potential depends on different things. We can calculate that stopping potential. We just need to apply a law of conservation of energy. When does it happen? It happens when even the most energetic electron gives away completely its energy to electric field. So work done by electric field is supposed to be equal to the maximum kinetic energy of the electrons. And we can use this expression if we need to calculate the value, right? The value of this potential difference we should apply. Well, this is an example of this kind of a calculation. The work function is given, and you know the wavelength 200 nanometers, hard to see, but 200 nanometers. So if you want to calculate the stopping potential, the first step is calculating the maximum kinetic energy of the electrons. That's what you do. And now, if you take this expression and you divide it by the value of electron charge, elementary charge, this should give you the voltage you're supposed to apply to stop current. Now, the little trick in this calculation is that if you rearrange the variables, you get this combination, HC. And this combination, mass, Planck's constant times speed of light, has a convenient value if you use convenient unit. 1240 electron volts times a nanometer. So that makes our life easier because instead of converting nanometers into meters, we can use just nanometers. They cancel each other out. Now here, electron volts minus electron volts give electron volts. But by definition, 1 electron volt is energy of 1 electron traveling 1 volt potential difference. So if you get 1.9 electron volts and you divide it by the charge, that gives you 1.9 volts immediately. So you don't have to use many converting factors. 1240 divided by 2 minus 4.3, 1.9. And it gives you volts.